Okay, so we left off by, in the middle of this problem, middle of example 4, we were finding integrals by interpreting each in terms of areas. And with the one on the left, we said that that function represents the positive half, the upper half of a circle.
Do they normally just come out on its own, or do you have to push buttons?
Since the limit of our integral is from x equals 0 to 1, we are only looking at this portion of the circle, which is exactly a quarter of a circle. So we said the area of this circle, since the radius is 1, would be pi times the radius squared, and then we would divide by 4 because we have a quarter of a circle. I asked you to take a look at the one on the right over the weekend, the extremely long weekend. And so that function is a line, the y-intercept of -1, an x-intercept of +1, and it extends all the way to, the limit of our integral is at 3. So this triangle here, this portion, because it's a triangle, we'd use 1/2 base times height, and we'd get 0.5 units. Now, because it's below the x-axis, we look at that as a negative area in most applications. Another way of looking at it is you have a width of +1 and a height of -1. We'll get more into that and how it applies to the integral in the next section of the chapter. This other triangle has a width of 2, and since the output here, this point would be 3, 2, it also has a height of 2. And so this would have an area of 2 units, and so we have a total of 1.5 units for our area. So in some cases, you can find that area very simply by looking at the geometric figure that it creates. In others, obviously, we've got to use more advanced tactics. So moving into the midpoint rule, this has sort of already been stated that the integral from a to b of f of x dx is equal to the sum of f of each x sub I bar, that's the new part, times delta x, or, delta x times the sum of all those f's. So that x bar is going to be defined as the midpoint of each interval, of each specific section. Now, we said earlier that we could take sample points in an intersection or in an interval, and we call them x sub I star. So what we're doing is we're just defining those sample points to be the exact midpoint of the interval. And so delta x is defined exactly the same way, but then x sub I bar is found by calculating the midpoint of the interval that it's on. Just to give a slightly different estimate. Usually a little more accurate, because when we construct our triangles, what happens is one side tends to be above the curve, the other side tends to be below the curve in a lot of cases. So it tends to balance out a little bit better. So for example, in example 5, we want to use the midpoint rule with 5 subdivisions, that's what n equals 5 represents, to approximate the integral from 1 to 2 of 1 over x dx. Now, what I'm going to do to approach this is kind of set up a little number line between 1 and 2 and break things up a bit. So if we're establishing 5 subdivisions, then they're going to come every 0.2 units. So the endpoints of our intervals are going to be 1, 1.2, 1.4, 1.6, 1.8, and 2. Which means the midpoints for each, okay, are going to be at 1.1, 1.3, 1.5, 1.7, 1.9. And so what the midpoint rule above tells us is that integral is equal to delta x times the sum of all the individual outputs at those midpoints and delta x is the width of each interval, which is 0.2. And so then we put in each of those midpoints. So we'd have 1 over 1.1, 1 over 1.3, 1 over 1.5, 1 over 1.7, and 1 over 1.9. So we're taking the outputs at each of those midpoints. We broke our integral into 5 sections. That's what the n equals 5 means. So that gives us an interval length of 0.2. And then we took the midpoint of each of those intervals as sample points. Now, we can also confirm that because of the way this function is designed, from x equals 1 to 2, we have the entire area above the x-axis. So we can confirm there that all of those should be positive. Eventually we'll get to a point where that's going to kind of take care of itself. But if we calculate this out, we get approximately 0.691908. And if you look above in that box for the midpoint rule, it does say approximate. The integral is an approximation, or is approximately equal to that midpoint setup. Until we get into really defining how the integral works, we're not going to get an exactitude. So before we get into how we actually apply those, we're going to look at some of the rules of integrals. First of all, the integral from b to a is equal to the opposite of the integral from a to b. So if you reverse the order of your interval, you actually get an opposite value. It seems kind of counterintuitive because you're taking an area under the curve between a and b. Why does it matter if you start at one end or go to the other? But when we get into the calculations of definite integrals, it's going to make a whole lot of sense. But essentially what happens is our delta x changes from b minus a over n to a minus b over n. And we should be able to see that those are opposites. So when we plug that back into the integral formula, it changes the sign. All right, the integral from a to a is always 0. If the two limits of your integral are the same, the area under the curve would be 0 because you're just looking directly under that line. You're not taking any width. Okay? So if there's no width, you have no area. Next, the integral of a constant is equal to the constant times the width of the integral. Okay, if you think about that as a graph, all right, if c is a constant, then you've got a horizontal line. And so the area between 2 points would be whatever this length is, b minus a, times whatever this height is, c. the integral of a sum of two functions is equal to the sum of the integrals as long as we keep it over the same intervals. Okay? Because if you think about when you're adding two functions, what you're doing is you're boosting one above the other. So if I had, let's say c is one of my functions just to keep the same picture, and here's another function, okay, I can take the area between each of them and put them together. Okay. When you have a constant multiple of a function, it's equal to the constant times the integral of that function. It's just boosting the height of that function, so it's just multiplying it a bit. And when you put 2 and 3 together, where c is a negative number, if you put 2 and 3 together, you can get 4. That sounds like really bad math. Put 2 and 3 together and get 4. But you put the second and third rule together, you get the fourth rule. When you take the integral of a difference of two functions, you get the difference of the two integrals. And the last one there for now, number 5. The integral from a to c plus the integral from c to b is equal to the integral from a to b. So if they share an endpoint and we sandwich those two sections together, we get the area of the whole section. That goes back to basic geometry. When you add two areas, you get the area of the compound figure. So we're going to use this to slowly break apart these functions here. Let's see. Oh, I got one more set. I thought I saved that for later, but that's okay. We'll cover that right now. Comparison properties of the integral. If a function is positive over the interval from a to b, then its integral is positive. If it's entirely above the x-axis, then the area is positive. If f of x is bigger than g of x, then its integral is bigger than g of x because it's creating more area between the function and the x-axis. If f of x is between some minimum and maximum value over a to b, then its integral is between that minimum value times the interval and the maximum value times the interval. Essentially, when I take and split this up, if I have a function always staying between some little m and some big M, then the area under the curve has got to be between this area and this area. It's got to be somewhere in the middle there. That's all that's saying. All right, so example 6, we're going to use some of these properties to break things up. So the first thing we would want to apply is the sum property, property number 2, which says I could split this into integral from 0 to 1 of 4 dx plus the integral from 0 to 1 of 3x squared dx. Then I can use property number 3 to pull that 3 out front. And based on property number 1, okay, if this is our C, this is our B, this is our A, then that equals C times B minus A, which is 4 times 1 minus 0, giving us just 4 for that section. Now, in the next section, we're going to learn an easy way to find this integral, but we have already calculated this in this section. An example, where was it? Yeah, maybe it was last section. But we did already calculate this in this chapter. couple of times. There we go. In example 1 and example 2 of the last section. And we said that the integral from 0 to 1 of x squared is 1/3. And so that section gives us a total of 1 for a total area of 5. Any questions on that problem? All right, let's look at something slightly more abstract. Example 7 says, if it is known that the integral of f of x from 0 to 10 is 17, and the integral from 0 to 8 of f of x is 12, find the integral from 8 to 10 of f of x. Now, at first blush, this might seem kind of confusing, but when we combine it with property number 5, this should become really simple. So property number 5, reinterpreting this with numbers, says that the integral of f of x dx from 0 to 8 plus the integral of f of x dx from 8 to 10 would equal the integral from 0 to 10. And remember, when we put two intervals together that share an endpoint, we get the whole integral. And so all we got to do is plug in the numbers that they give us and figure out what this must equal. So what would the integral from 8 to 10 of f of x dx equal? They give you this. They give you this. All you got to find is this. What would it be? Five. Okay. So the integral from 0 to 10 is 17. That means the whole area from 0 to 10 is 17. The portion from 0 to 8 is 12. So the missing piece must be 5. Okay. Essentially, there was some curve between 0 and 10 so that this whole area was 17, but this area up to 8 was 12. So that means that this remaining portion here must be 5. That's really all it's saying. Any questions on that problem? All right. Lastly, let's look at example 8. For example 8, we're going to use property 8. So let me rewrite it here. If f of x is bound between two values, for a certain interval, then the integral of f of x from a to b is between little m times b minus a and big M times b minus a, which would be basically applying the integral to the little m and the big M following property, what number was it? Number 1. Okay, you've got a constant times the length of that interval. So our goal in this case then is to sandwich this function between a minimum and maximum value so that we can use those to approximate the integral. Now, because we know this is a decreasing function, okay? We know that because that exponent is negative and x squared is always positive, so that's going to be decreasing. Because we know that, we know that on that interval, its highest value is going to occur at the left-hand side. Let me explain that a little more clearly. Because this function is decreasing, the highest possible value is going to be at the left side of the interval because it's decreasing from there. So the highest value is going to be at e to the negative 0 squared, which is just 1. Okay? That's the highest value it's going to reach. So that's going to replace our m. Also, since it's decreasing, the absolute lowest that it could reach will be at the right-hand side of its interval. Okay, that's going to be the lowest. So there's our big M, there's our little m. So our absolute lowest is e to the negative 1 squared, or 1 over e if you want to write it that way. That's going to be our little m. So that tells us that our integral from 0 to 1 of e to the negative x squared dx is somewhere between e to the negative 1 times 1 minus 0, which is just 1, and e to the 0 times 1 minus 0. So using our calculator, we know that it must be somewhere between those two values, which are which on the right-hand side is exactly equal to 1. On the left-hand side is approximately 0.367. Now, if you put that in your calculator, you probably saw that it's 0.3679, and you would think that we round up. But because that's a lower estimate for our integral, we can't round up because that might bring us past the estimated value. So we have to always round down in those cases. So that always rounds down. That's why we have 0.367 and not 0.368. Any questions on how that works? If that were an increasing function, we would end up switching essentially. Our lowest possible value would be on the left-hand side of the interval. Our highest would be on the right. But all we got to do is kind of look at the graph, look at the function itself, and use that to find some maximum minimum values. All right, so if there's no questions on 3.2, are there any of those before we move on? All right, so here's where it's going to start to pick up speed a little bit, get a little bit easier in its approach. First of all, the evaluation theorem. If f is continuous on the interval from a to b, then the integral from a to b of little f of x dx is equal to big F of b minus big F of a, where big F is any antiderivative of little f. That is big F prime equals little f. Now, I want to just explain something right here. That word right there. Big F is any antiderivative. So normally when we find the antiderivative and we're talking about a particular derivative, we have a plus c, some unknown value. Now the thing is, we can use any antiderivative, which means we could use any value for c. But the key is both of these have to be the same antiderivative. So that means they've both got that plus c. And so when we subtract the two functions, those plus c's cancel out anyways and don't make an impact on the integral. So that allows us to skip through. Now, I left some space open for the proof and demonstration of the evaluation theorem. We don't really have time the way we've been going, so we're going to skip over that and jump right into how we apply this. So when we're evaluating an integral, technically we're using general antiderivatives with a plus c, but because both ends of them would cancel out, we essentially ignore them and don't even bother. So the first thing we want to do in order to evaluate this integral is to find the antiderivative of e to the x. So if little f of x is e to the x, what is big F of x? What is the antiderivative of e to the x? I know we've had a long break, but somebody's got to remember what the antiderivative of e to the x is.
E to the x.
E to the x. Now again, technically we would add a c, but since we're subtracting two antiderivatives in the end, those c's are going to cancel out anyway, so we don't bother including them. So all we have to do then, if we look back at that rule, is we take f of the upper limit of our integral, which is 3 in this case, minus f of the lower limit. Now we have a particular way of writing this. What we would say is that if I go back up here, I would say this is equal to e to the x, that's my antiderivative, evaluated from 3 to 1. That's what that little bracket means. And basically, just like it says right here, I plug in a 3 and I plug in a 1 and I subtract them. So this is equal to e to the third minus e to the first. Now, we actually did one like this using the longer method and the definition of the integral in the last section. Hopefully you see this is a lot faster than breaking it up into little intervals and using some summation rules and things like that. Any questions there? Okay. Let's take a look at the next one. Find the area under the cosine curve from 0 to b, where b is between 0 and pi over 2. So as you notice here, they don't tell you exactly what b is. So that means our integral, our final answer is probably going to involve that variable. So the reason that they put this in there, it goes back to the sign of trig functions. If we know what quadrant we're looking at, then we know exactly what sign we should be looking at, whether it's positive or negative. So what we're doing is we're finding some area equal to the integral from 0 to some b of cosine x dx. It's going to be the area under the cosine curve. So what is the antiderivative of cosine x? What's the antiderivative of cosine? Sine. So we're going to take and we're going to evaluate sine x from 0 to b, which we do by plugging in b, and we know that's going to be a positive value because b is in the first quadrant. minus sine of 0. And what's sine 0 equal to? What's sine of 0? 0. So this is just equal to sine b. So if we knew exactly where we were ending, we could find the area of the curve, or underneath the curve of cosine. Which is kind of important because of the applications of trig functions, and also really important because otherwise you have these irregular shapes under trig functions that you've got to find areas for. We don't really have any other method for which to do so. So the integral becomes really essential. All right, we have this notation here. This is really just a notation, not a rule or a law or anything, for what we call the indefinite integral. The difference between the indefinite integral and the definite integral is that the definite integral has endpoints of evaluation. The indefinite does not. So essentially what the indefinite integral is giving you is an antiderivative. It gives you a function, or if we don't throw a c on there, it gives you, or if we do throw a c on there, it gives you a family of functions is what it does. So you could then use the indefinite integral to find a definite integral if you were given an interval to do that with. So that's key. But like I said, not a huge rule or property thing there, just a notation point. All right, and we also have a table of indefinite integrals here. Some of those include some of the rules that we learned in the last section, but a lot of them are just the antiderivative rules that we learned in the end of chapter 4 for how to find an antiderivative. So you notice they're essentially the same, an antiderivative and an indefinite integral. The indefinite integral of e to the x is e to the x plus c. The indefinite integral of sine x is negative cosine x plus c. So these will come in handy when you're calculating indefinite and definite integrals. So if we look at example 3 here, this is asking for an indefinite integral because we have no limits on our integral there. So it's essentially asking for an antiderivative. And we can use all of our integral rules to apply to that. We can split it up into two pieces. We can bring the coefficients out front. Oops. Can't write it twice, though. And then we can start to apply our rule. So the antiderivative of x to the 4th requires that we bump our exponent up by 1, and then we multiply by the reciprocal of that new exponent. What is the antiderivative of secant squared x? Tangent. Very good. And so we're going to throw a c on the end here. And the only thing left to do is simplify. So we have 2x to the 5th minus 2 tan x plus c. That's our indefinite integral, which is also our antiderivative, essentially. And what you're going to find through practice is that a lot of these are going to become very easy to calculate quickly. So let's do one more. We got just a few minutes left in class. We'll do one more, and we'll be done for the day. And by the way, we're looking at an exam next Wednesday. That will be the Chapter 5 exam, which will only cover through 5.4. And then you're having the final the Tuesday, June 12th. So that's the first day of Regents testing. All right, so we start by taking the antiderivative. What would be the antiderivative of x to the third? One-fourth x to the fourth. San Antonio. So we bump that exponent up 1, multiply by the reciprocal of the new exponent. What about the antiderivative of 6x? Or negative 6x, however you want to look at it.
Negative 3x squared.
Negative 3x squared. So we're bumping that exponent up by 1, which means we got to multiply it by 1/2, bringing that 6 down to a 3. So you can look at it as the integral of, or the antiderivative of 6x and throw the negative in there, or look at it as the antiderivative of negative 6x. It's up to you. So we're going to evaluate that from 3 to 0, which means all we have to do is plug in 3, and then plug in 0. Now in this case, that 0 is not going to have any impact. Oops, missed an exponent there. Sometimes it does, so be careful. Don't assume that the 0 will always give you a 0. So we have 81 over 4 minus 27 minus 0. Which gives us negative 27 over 4, or negative 6.75. Does that make sense? Are there any questions? All right, so we'll continue on Thursday with evaluating definite integrals. Hopefully Monday and Tuesday we can take care of 5.4 and have a review session before next Wednesday's exam. So keep an eye out for the homework online. Keep up with that and make sure you're ready for next week. If you have any questions, again, feel free to email me at any time. Have a great day.